Nuclear magnetic resonance spectroscopy. Over the past 50 years, nuclear magnetic resonance spectroscopy, commonly referred to as NMR, has become the prominent technique for determining the structure of organic compounds. It is used for structure determination of organic compounds. Of all the spectroscoping methods, it is the only one for which a complete analysis and interpretation of the entire spectrum is normally expected. Although large amounts of samples are needed than for mass spectroscopy, NMR is non-destructive, and with modern instruments, good data may be obtained from samples weighing less than a milligram. To be successful in using NMR as an analytical tool, it is necessary to understand the physiological and physical principles on which the method is based. The nuclei of many elemental isotopes have a characteristic spin. They have a characteristic spin. Some nuclei have integral spins, some have fractional spins, and a few have no spin. Isotopes of particular interest and use to organic chemists are hydrogen, carbon, iron, phosphorus, all of which have characteristic spin is equal to half. Since the analysis of this spin state is fairly straightforward, our discussion of NMR will be limited to this and other characteristic spin is equal to half nuclei. For a table of nuclear spin characteristics, just the following features lead to the NMR phenomenon. Nuclear magnetic resonance spectroscopy. A spinning charge generates a magnetic field as shown by the animation on the right. The resulting spin magnet has a magnetic moment proportional to the spin. In the presence of an external magnetic field, two spin states exist, plus half and minus half. The magnetic moment of the lower energy plus half state is aligned with the external field, but that of the higher energy minus half spin state is opposed to the external field. Note that the arrow representing the external field points north. Spin energy states are there. The difference in energy between the two spin states is depend on the external magnetic field strength and is always very small. What is very small? The difference in energy between the two spin states. The following diagram illustrates that the two spin states have the same energy when the external field is 0 but diverge as the field increases. At a field equal to Bx, a formula for the energy difference is given. Like, remember, characteristic spin is equal to half and mu is the magnetic moment of the nucleus in the field. So when we represent a graph where y-axis is representing E, energy, and x-axis is there which is representing the magnetic field, then there will be a cone produced in the y-axis, and that difference in length between those two cone lines will be delta E, that is the mu b x by I, and plus half will be represented on the top and minus half will be represented on the top and plus half will be represented on the bottom side. Strong magnetic fields are necessary for NMR spectroscopy. The international unit for magnetic flux is Tesla. The Earth's magnetic field is not constant but is approximately 10 raised to minus 40 at ground level. Modern NMR spectrometers are powerful magnets having effects of 1 to 20 T. Even with these high fields, the energy difference between the two spin states is less than 0.1 CAL per mole. The Earth's magnetic field is not constant, but it is approximately 10 raised to minus 4 Tesla at ground level. Modern NMR spectrometers use powerful magnets having fields of 4 to 20 T. Even with these high fields, the energy difference between these two spin states is less than 0.1 col per mole. To put it in perspective, recall that infrared transitions involve 1 to 10 kilocalorie per mole and electronic transitions are nearly 100 times greater. For NMR purposes, This small energy difference is usually given as a frequency in units of HSZ megahertz. For NMR purposes, the small energy difference is usually given as a frequency of units of megahertz, ranging from 20 to 900 megahertz depending on the magnetic field strength and the specific nucleus being studied. Irradiation of the sample with radio frequency energy corresponding exactly to the spin state separation of a specific set of nuclei will cause excitation of those nuclei in the plus half state to the higher negative half sign state. Note that this electromagnetic radiation falls in the radio and television broadcast spectrum. NMR spectroscopy is therefore the energetically mildest probe used to examine the structure of molecules. The nucleus of a hydrogen atom, the proton, for spin half nuclei. The energy difference between the two spin states at a given magnetic field strength will be proportional to their magnetic moments. For the four common nuclei noted above, that the magnetic moments are given, and these moments are in nuclear magnetons, which are given a value. The following diagram gives the approximate frequencies that correspond to the spin state energy separations for each of these nuclei in an external magnetic field of 2.35 T. The formula in the colored box shows the direct correlation of frequency energy difference with magnetic moment. Planck's constant is given. Protein NMR spectroscopy will be here. Protein NMR spectroscopy. This important and well-established application of nuclear magnetic resonance will serve to illustrate some of the novel aspects of this method. This important and well-established application of nuclear magnetic resonance will serve to illustrate some of the novel aspects of this method. To begin with, the NMR spectrometer must be turned to a specific nucleus, in this case the proton. The actual procedure for obtaining the spectrum varies, but the simplest is referred to as the continuous wave method. A typical CW spectrometer is shown in the following diagram. A solution of the sample in a uniform 5 mm glass tube is oriented between the poles of a powerful magnet and is spun to average any magnetic field variations as well as tube imperfections. Radio frequency radiation of appropriate energy is broadcast into the sample from the antenna coil, colored red. A receiver coil surrounds the sample tube, and emission of absorbed energy is monitored by the dedicated electronic device. A solution of the sample in the uniform 5 mm glass tube is oriented between the poles of a powerful magnet and is spun to average any magnetic field variations as well as tube imperfections. Radio frequency radiation of appropriate energy is broadcast into the sample from an antenna coil, colored red. A receiver coil surrounds the sample tube, and emission of absorbed RF energy is monitored by dedicated electronic device and a computer. An NMR spectrum is applied by varying or sweeping the magnetic field over a small range while observing the RF signal from the sample. An equally effective technique is to vary the frequency of the RF radiation while holding the external field constant. For a description of the pulse, so when we just look at the structure, sweep generator will be there, magnetic poles are there, radio frequency transmitter will be there, sweep coils are there, spinning sample tube will be there, sweep coils are there, radio frequency receiver and amplifier will be there, and magnetic pole will be there. So these portions are there. So as an example, consider a sample of water in a 2.3487 T external, T in the sense Tesla, magnetic field irradiated by 100 megahertz radiation. If the magnetic field is smoothly increased to 2.3488 T, the hydrogen nuclei of the water molecules will at some point absorb the energy and a resonance signal will appear. An animation showing this may be achieved by clicking the field sweep will be repeated 3 times and the resulting resonance traces down to red. For visibility, the water proton signal displayed in the animation is much broader than it would be in the actual experiment. So B will be representing a y-axis, Tesla current will be there. So increasing magnetic field at frequency increases into the right side. Since photons all have the same magnetic moment, we might expect all hydrogen atoms to give a resonance signal at the same field or frequency values. Fortunately for chemistry application, this is not true. By clicking the show different problems button under the diagram, with the exception of water, chloroform and sulfuric acid, which are examples are liquids, all the other compounds are measured as gases. Why should the proton nuclei in different compounds behave differently in the NMR experiment? The answer to this question lies with the electrons surrounding the proton in covalent compounds and ions. Since electrons are charged particles, they move in response to the external magnetic field so as to generate a secondary field that opposes the much stronger applied field. This secondary field shields the nucleus from the applied field, so BO must be increased in order to achieve resonance absorption of energy. BO must be increased to compensate for the induced shielding field. In the upper diagram, the compounds that give resonance signals in the higher field shield of a diagram is shown, have proton nuclei that are more shielded than those on the lower field left side of the diagram. The magnetic field range displayed in the above diagram is very small compared with the actual field strength. Only the magnetic field range displayed in the above diagram is important. It is customary to refer to small increments such as this in units of parts per million. The difference between 2.348T and 2.3448T is therefore about 42 ppm. Instead of designing a range of NMR signals in terms of magnetic field differences as above, it is more common to use a frequency scale, even though the spectrometer may operate by sweeping the magnetic field. Using this terminology, we would find that may operate by sweeping the magnetic field, give proton signals shown above 10 over a 4.200 Hz range. Most organic compounds exhibit proton resonances that fall within a 12 ppm range. It is therefore necessary to use very sensitive and precise spectrometers to resolve structurally defined sets of hydrogen atoms within this narrow range. In this respect, it might be noted that the detection of part per million difference is equivalent to detecting a 1 millimeter difference in distance of 1 kilometer. Chemical shift, unlike infrared and UV visible spectroscopy, where absorption peaks are uniquely located by a frequency or wavelength, the location of different NMR resonance signals is dependent on both the external magnetic field strength and the RF energy. Since no two magnets will have exactly the same field, resonance frequencies will vary accordingly, and an alternative method for characterizing and specifying the location of NMR signals is needed. This problem is illustrated by the 7 different compounds, and the 7 resonance signals are distinct and well separated. When we learn about this, one method of solving this problem is to report the location of an NMR signal in the spectrum relative to a reference signal from a standard compound added to the sample. Such a reference standard should be chemically unreactive and easily removed from the sample after the measurement. Also, it should give a single sharp NMR signal that does not interfere with the resonances normally observed for organic compounds. Tetramethyl silane, usually referred to as TMS, meets all these characteristics and has become the reference compound of choice for proton and carbon NMR. What is that? Tetramethyl silane, tetramethyl, silane, usually referred to as TMS, meets all these characteristics and has become the reference compound of choice for proton and carbon NMR. Since the separation or dispersion of NMR signals is magnetic field dependent, one additional step must be taken in order to provide an unambiguous location unit. This is illustrated for the acetone, methylene chloride, and benzene signals by clicking on the previous diagram. To correct this frequency differences for the field dependence, we divide them by the spectrometer frequency. The resulting number would be very small since we have dividing that with hertz by megahertz. So it's multiplied by a million. The compounds referred to above share two common characteristics. The hydrogen atoms in a given molecule are all structurally equivalent, averaged for fast conformation equilibria. The compounds are all liquids, save for septane, which boils at 9 degrees Celsius, and a liquid in a bath. The first feature assures that each compound gives a single sharp resonance signal. The second allows the pure neat substance to be poured into the sample tube and examined in an NMR spectrometer. In order to take the NMR spectra of a solid, it is usually necessary to dissolve in a suitable solvent. Early studies used carbon tetrachloride for this purpose, since it has no hydrogen that could introduce an interfering signal. Unfortunately, CC4 is a poor solvent for many polar compounds and also is toxic. Deuterium labeled compounds such as deuterium oxide, chloroform, benzene, etc. are now widely used in NMR solvents. Since the deuterium isotope of hydrogen has a different magnetic moment and spin, it is invisible in the spectrometer tuned to protons. So we will be using deuterium labeled compounds.